Welcome to the Life Cycle of the Stars. I'm your host, Patrick Beck. We begin our journey of the stars with a nebula. This is the beginning of our first star, Agath A. This will also be where our second star will originate, Agath B, but in a different nebula. From now on, we're going to focus on Agath A, as both stars will follow a similar path, but we'll differentiate them when they go their separate ways. So now, let's watch as our nebula begins to spin, and as it spins faster, it is also creating a gravitational force upon itself, and now it will begin contracting until it's so small that we can sufficiently call it a protostar. However, due to the compression of this nebula, friction and other forces have caused the protostar to heat up to over 15 million Kelvin. Also, as a result of this extreme compression, hydrogen atoms are being pushed so close together that they're going to begin bonding together and forming helium. And this means that nuclear fusion has begun within our stars, thus putting them into the main sequence. Now, these stars are in their middle-aged life, and this is where they will spend the majority of their time. They will continue to use nuclear fusion to bond hydrogen atoms together, and as a result remain the same size, as the gravity pushing inward on our stars will balance out with the energy being pushed outward through the nuclear fusion, therefore making it balanced. And now to the HR diagram, where we can see that our stars are right in that middle-ish area on that slant. Later then, when their fuel begins to run out, their outer layers will begin to expand and cool down. This means our stars have entered the red giant phase. The stars will enter this phase because they've used up so much of their hydrogen that the amount of nuclear fusion able to be taking place in the core has decreased considerably, meaning the outside gravitational force on these stars will cause their cores to contract, and as a result, get even hotter. And this gives our stars just enough heat to continue nuclear fusion within their cores, allowing what little energy is left after all of the chemical bonds to expand the outer layers, making the stars larger. And now back to the HR diagram again, where we can now see that our stars are right in the middle, just above where they were previously in the main sequence. However, later the stars will begin changing again, and so this is where we will split our two stars. So, we'll start with Agath A. Now, Agath A is considered a low-mass star, and is therefore going to end up as a black dwarf. But, before that happens, let's see how it gets there. Now, Agath A will continue to lose mass as it now ends up fusing helium into carbon and oxygen, basically meaning that there isn't enough hydrogen in its core to bond together and form helium. And as a result, there's going to be less energy to push out to counteract gravity, making gravity cause the core to contract and heat up even more, like in the red giant phase, because there's less and less energy. Except this time, the outer layers are going to end up expanding so much that they will end up just drifting away once they leave Agath A's gravity, turning the outer layer into a planetary nebula, where it will form new stars. And as the core gradually uses up even more of its fuel, it will begin to cool and turn into a white dwarf, which is just the core of the star. And eventually, Agath A will continue to cool and then become a black dwarf, which is a white dwarf which has used up all of its fuel and is no longer illuminated. Now, before we begin to look at Agath B's cycle, we'll go back and take another look at where Agath A was during the white dwarf phase. And it is right there in the middle of the bottom diagram. And now, we can take a look at Agath B. It, on the other hand, is considered a high mass star, the opposite of Agath A. And right now it's at the red giant phase. So let's see what's going to happen next. Now, Geth B will continue to swell until it becomes a supergiant. It won't stop like a Geth A did. And before we see what happens next, we're going to go ahead and go back to the HR diagram real quick. And we're going to see that a Geth B has actually gone even farther up the diagram, almost reaching the top. And as the core contracts and causes what little energy it has left outward, expanding the outer layer, this time something different is going to happen that is unlike anything a Geth A ever did. A Geth B will continue to grow until its nuclear fusion has ended up bonding iron atoms. And the problem with iron is that its weight is so massive compared to the lightweight hydrogen that it was burning, that it will end up using so much energy bonding the iron that it won't have nearly enough energy to counteract the gravity. Meaning that the gravity is going to start to crush the large star, and quite harshly, thereby creating a supernova. However, during this supernova, Geth B could have two different outcomes, so let's investigate those. Now, Geth B might have been small enough before the supernova that its remnants will just become a neutron star. A very tiny star about the size of Earth filled with neutrons from the original Geth B. Or, a Geth B might have been large enough before the supernova that when it collapsed, it formed a black hole, which is basically what its title states. A black hole of nothingness, where not even light can escape. And that has been the life cycle of the stars by Patrick Beck. So this has been fun, and goodbye from me and Morgan Freeman.